The topic today we are going to discuss is about the A to D converter and the D to A converter. So already we have seen the same topic resemblance to this as voltage to current converter and the current to the voltage converter. So wherever we require the current, so in that presence of that we get an output as an voltage, we need to convert that voltage to the current factors. So in this we are going to see an analog signal is converted to a digital signal, and the digital signals to be converted to an analog signal. So that's why we call it as an ADC or DAC. Okay. So in this the main general block diagram of this A to D and D to A converter is that first thing is a plant. So from this it may be a process plant or may be the industry. So here we require some physical quantities like voltage, current, temperatures. So these are the inputs, these are the outputs. So the thing from that plant we require will get some physical quantities. That physical quantity is processed through a sensor or transducer which produces an outputs like an electrical output like voltage, current, temperature, pressure, whatever may be the process plant. So these signals are analog signals. So this analog signals are passed through the anti-aliasing filter. So this filter, usually the filter removes the unwanted signal. In this case of this anti-aliasing filter, it removes some particular frequencies. There will be a limit in the frequency of the signal. So we call this as a band limited analog signal. So we might have studied filters like low pass filter, high pass filter, band pass filter and band stop filter. So here the band is like a specific regions like 50 kilohertz to 1 megahertz or 1 megahertz to 10 megahertz. So like that a band limited analog signal is processed with the sample and hold circuit. So here we produce an analog signal, that too is like a partial digital signal. So these analog signal is purely we have to convert to digital signal. We go for this A to D converter. So he will be getting a discrete digital signal as the output. So that stored in the computer, whenever we require, we will be processing through the digital signal processor. From that a digital binary signal is processed as the output is given to the input as the digital to analog converter. So here this A to D is just an opposite to this D to A converter, where we give a binary signal as the input to the digital converter which produces an analog signal. So that analog signal will be like a staircase signal. That staircase is like a ramp signal. So in this condition we are going to use that smoothing filter to get an analog signal. The smoothing filter, here the sampling frequency is taking place, that the input signal, the smoothing frequencies, that sampled frequency is Fs, which is greater than the twice the measured frequencies. So it will be the maximum of that frequency signal. So in that sample frequency is processed and the digital output is passed through the smoothing filter, which reduces the effect of quantization noise. So next we are going to separately deal with the D to A converter and the A to D converter. So in general where we use this application is shown in this block diagram. So this next topic is basic digital to analog converter, DAC techniques. The basic DAC, the DAQ is nothing but your data acquisition, but in case of DAC is nothing but a digital to analog converter. Here the input signals are binary words and the output will be an analog signal. So here it's a digital to analog converter. We have the inputs like D1, D2 up to D power n, Dn, where D1 starts with the most significant bit and Dn will be the least significant bit. This is considered as the general term, we call it as a binary word D. and we have the reference voltages plus VR, and it is connected between this plus terminal and minus terminal, and the output is taken across the voltage. So everywhere the input bit, they have a reference voltage, these things to be mentioned, and the output is taken across the voltage signal. Here it should be an analog waveform. So as I mentioned, that input is an n-bit binary word, and VR is your reference voltage. With these two input terminals, we produce a digital to analog converter, produces an output signal as an analog signal. So here that V0 is the written mathematically, the DAC expression should be written as mathematically as V0 is equal to K into VFS, where Fs is the full scale voltage. So V0 is equal to K into, the K is the scaling factor, and VFS is the full scale voltage, which is multiplied with the binary weighted. So D1 to the power 2 power minus 1 and D2 to the power 2 power minus 2, like that it goes on for Dn 2 power minus n. So here the D1 with the weighted resistor of your voltage, full scale voltage is D1 is equal to VFS by 2. In case of Dn, we go for the weight VFS by 2 power n. So this is the basic digital to analog converter technique uses the expression as V0 is equal to the scaling factor is multiplied with the full scale voltage, and the binary bit is multiplied with the resistors binary values, right. D1 is equal to as the most significant bit. Whenever in this A to D or D to A conversion, we go for the D1 bit. That D1 bit will stands for the D, by default it will be in the most significant bit. So here we have the three types of methods used in digital to analog converters are weighted resistor, R2 2R ladder, and the inverted R2 2R ladder. So here the weighted resistor and the R2 2R ladder is there in our syllabus. So the weighted resistor, we give some multiplying factors of weight to that resistor part. The weighted resistor, digital to analog converter. So this is the operational amplifier. Here the inverting terminal is connected with the resistor values, whereas the non-inverting terminal to be grounded, and we have a feedback resistor RF. So the output voltage produced at the V0. So far we have studied in this part alone, it's like inverting, non-inverting with output voltage. In case of this digital with the weighted resistor, so we have a resistors to be connected parallelly with a current flow of I1, I2, I3 up to IN, and we have the resistor values 2 power 1 into R. This is the resistor multiplied with some values that we call it as the resistor, weighted resistor. So 2 power 2 power into R, 2 power 3 into R, like that. If goes on 2 power n minus 1 into R, 2 power n into R. Here I have given the connections, it is with the grounded terminal, where we need it, the connections will be connected to that minus VR, that is the reference voltage. So that's what quoted, it's an N electronic switches. So these switches, or we call it as a single pole double throw switch. These are the types of the switches, and this D1, D2, D3 are controlled by these binary input values. So in this, if the binary input value is 1, it is connected to that resistor. See here in the D1 part, it's considered as the most significant bit. It is connected to the ground terminal. So the binary input is taken as 0. Usually by the thing binary, when we discuss, it deals with two numbers, zeros and ones. Then now it is connected to this grounded terminal, so I can make my this D1 as 0, here this D2 as 0. And the next thing, consider that as D3. Here it is not connected to that ground terminal, it is connected to that VR. negative reference voltage terminal. So here if the binary input is connected to a particular switch is 1, it connects to the reference voltage. If the input is connected to 0, it connects to the ground terminal. So I can write the expression I0 is equal to I1, I2, I3 up to In. Here it can be written as I1 as current can be replaced as V by R. So here for this the reference voltage is VR and the current flow in this I1 is 2 power 1 into R. Then D1 plus in case of the current flow in R2, then I can write VR by 2 power 2 into R into with D2 terminal, plus if I goes on, then I can write VR by 2 power n into R dn. So now I can take that I0 as the expression as VR by 2 power or else R terminal. So I can mention D1 by 2 plus D2 by 2 power 2 plus I can write Dn 2 power n. So this can be written as VR by R of D1. So I can make this 2 denominator 2 can be placed in the numerator as 2 power minus 1, D2 2 power minus 2, for Dn 2 power minus n. This is the value of that output current I0. So this is the value, whereas I have to find the output voltage. So I can write that output voltage is equal to I0 into RF. So this I0 value is equal to VR by R into that value. So I can make it RF D1 2 power minus 1 plus D2 2 power minus 2. Like that, if I write for D power n minus 1, it is 2 power n minus 1 plus Dn 2 power minus n. In this, I have to write this expression V0 is equal to K into VFS into this factor. So this factor remains as such, and that K and VFS. So here that VFS I can mention it as VR. This is replaced with VFS is equal to VR, and as I mentioned that K is a scaling factor, so I can make my RF value as R, then I can replace RF by R as R, and R is equal to 1. So I can write this expression RF is equal to R and R by R is equal to 1. So this expression V0 is equal to VFS divided into K of these values. We can replace that. That resembles your basic DAC techniques. This is the expression to be altered in this weighted resistor DAC. So in this condition, I can say the digital input codes. So when we draw, now we know that the inputs are digital and the outputs are the analog technique. So when we go for this input code, we start with 0 0 0, that corresponding voltages will be seen. So here for 0 voltage, what will be the output is also 0 in terms of pulse. Then 0 0 1, it is started with 1 by A VR. So in that condition we have to write 0 0 1. Wherever it comes, it will be like a staircase. It's like a staircase, or we call it as a ramp signal. So coming to that R2 to R. So the first concept we have studied is weighted resistor digital to analog converter. The second one, it's a R to 2R ladder DAC. So here we are going to use only the two resistance like R and 2R. It's like a ladder concepts. So the same concept, it's an operational amplifier. The non-inverting terminal is to be grounded, and there we had and only the feedback resistor as RF. So here we have used the 2R resistor, and we have R resistors in series, and the 2R to be both those things are series. It's like a parallel one, it is connected. In the final, it's like a to be grounded. Then we give connections to that negative reference voltage. Here we can give whenever the thing it is connected to the VR terminal, the binary bit as 1. If it is connected to the ground terminal, it will be marked as a 0. So in that zeros terminal and the D1 input binary word is at the MSB, and whereas the D3 will be at the LSB side. Okay, so why we go for this technique? So in this technique, we are not going to prefer the wide range of resistors. There we have used like a resistor into 2 power 1, 2 power 2, or 2 power n minus 1, or 2 power n number of weighted resistor value. So here the weighted range of wide range of resistors are avoided, and we have used that R and 2R concepts. So only the two values of resistors are used, and the resistor will be in the range of R is equal to 2.5 kilo ohms to 10 kilo ohms. That will be the range of the R value to be preferred. So if the value of R is preferred, that will be multiplied with R, which gives multiplied with 2, it gives the 2R value. So now I have made this as the connection. I have D3 as 0, it's a ground terminal. D2 as 0, it's ground terminal, and D1 as 1, it is connected to that negative reference voltage. So the thing, here the 2R connected, and here the 2R is connected, here again 2R and 2R. So 4 2Rs are connected here. The first 3 terminals are connected with the ground, and the last one here, the MSB, is connected with the reference voltage, and the series R is connected, and again the same circuit resembles here. So now we are going to calculate the output voltage based on this reference voltage. So it is like you have to make, this will be like what connection? Series connection. If you connect, it makes a 2R plus 2R, or if it is a parallel connection, 2R into 2R by 2R plus 2R. Like that, we have to reduce the circuit at the terminal C. You have reduced these expressions, and we get a simplification like 2R into R divided by 3R. So 2R, it's like a 2 by 3 R. Then voltage is like minus VR. Then we are going to add it with this. So minus VR into 2 by 3 R divided by 2R plus 2 by 3 into R, which gives minus VR by 4 as that expression. So in that, the output voltage up to this, we have calculated that reference voltage value reduced the expression as minus VR by 4, and we have another 2R resistor. Then we give one more resistor part. So the output voltage is minus 2R by R into minus VR by 4. So the output voltage is equal to VR by 2. Here I am going to substitute the VR value as the full scale voltage. So here the expression V0 is equal to Vf plus by 2. That's the concept in the R to 2R ladder diagram. So now, so far we have seen as a digital to analog converter. In the digital to analog converter, we give the digital input by bit as a word as a D1, D2, Dn. It's the common word, we call it as 8 bits. It's like a D representation. So that is to be passed to the digital to analog converter with another inputs as the reference voltage. It produces an output as an analog signal. So there we have seen two types. One is the weighted resistor and the R to 2R. So your weighted resistor is every time it multiplies some multiplying binary factors like 2 power 1, 2 power 2, or like 2 power n minus 1 with the resistor value to be multiplied. Whereas in case of your R to 2R, we will be preferring only the values either R and 2R. So in that R and 2R, that R should be in the range of 2.5 kilo ohms to 10 kilo ohms. Coming to the topic analog to digital converter. So, we know the concept analog to digital converter, the input signal is an analog signal and the digital will be an output signal. So, here this is the basic block diagram of the analog to digital converter. Here the analog input VA and the reference input is VR. So, it is like similar to your comparator concept. So, the comparator will compare VA is equal to or VA will be less than or the with other voltage and the VA will be greater than the reference voltages. Like that we have input voltage VA and the reference voltage VR, and the outputs will be like D1, D2, it's like an output binary word. Then we have the two commands like start of the command and the end of the conversation. So, when we are going to proceed with this comparator topic, every time we have to start with that command signal. Once it's started, the analog signal is compared with the reference signal every time and the output will be proceeded as the digital output. That's next. Like that subsequently it proceeds and we don't have any other options at that end, we will be going to that end of conversion topic. So, the thing that A to D is the opposite to that of DAC. So, here the analog input produces a binary word output D. So, in that condition your D will be like D1 2 power minus 1, D2 2 power minus 2 up to we go for n number of binary word Dn 2 power n. Sorry, it is like Dn 2 power minus n. Okay. So, where we can use this concepts like analog to digital converter. So, whenever we study the microprocessor and we go to interface with some kits, hardware kits, then we go for that microprocessor interfacing like LCD or LED displays. So, here again we can classify the analog to digital converters into two types. The one is direct type DAC, sorry. Direct type ADC and integrating type. So, in this direct type ADC, we have the four types. One is flash type converter, counter type converter, tracking or servo converter, and the fourth one successive approximation type converter. So, in this the flash converter is similar to your comparator concept, and the main most efficient method to be followed right now in recent trends is called as the successive approximation type. So, here the direct input ADC. When we talk about the direct input ADC, here we can discuss with the input voltage, that is your analog signal, and there will be an inbuilt reference voltage signal. Whereas the integrating type ADC, we have an analog signal as an input that will be converted into a linear signals and then it will be converted to a digital output. There will be an intermediate factor behind with the analog signal and the digital signal, that may be your time or the frequency factor. So, in case of your integrating type DSC, we have charge balancing and dual slope ADC. So, here we have the three concepts. In direct type ADC, we are going to discuss about flash type converter and the successive approximation type converter. Whereas in that integrating type ADC, we have two types. One is charge balancing and the other one is dual slope ADC. So, these three marked we are going to discuss in the coming chapters. So, next converter is the flash type converter, is nothing but a direct type converter. So, comparator. Okay, in this direct type, as I mentioned, discussing with the analog signal and the reference signal. So, it's the flash type is the very simple method to be used among this direct type ADC. So, here we are going to design an analog signals with the corresponding output signals. So, here we are going to use the analog input signal and the reference input signal. Here we have an operational amplifiers with 8 inputs like 1, 2, 3, 4, 5, 6, 7, 8. 8 operational amplifiers, 8 resistors, voltage divider concepts, and that 8 line to 3 line encoder is used. So we might have studied the concepts like max, Gmax, encoder, decoder, whereas the encoder topic we write 2 power n to n type encoder. So here a 2 power 3 to 3 lines are to be. The 2 power 3 is nothing but your 8 to 3 line encoder is designed. That means an 8 analog input signal is processed to produce a 3-bit code like a 000 to 111 concept. Okay, that's the code we can mention. So here we have an operational amplifier, and that operational amplifiers, the analog input VA is connected with this red lines. It is connected to that non-inverting terminal, and the reference voltage is connected to that inverting terminal. So this reference voltage is divided with the voltage divider. The concept there we can give directly the VR as the voltage for this operational amplifier, and for this operational amplifier it is one of totally we have 8 of there, 7 by 8 VR is given here, then 6 by 8, 5 by 8, 4 by 8, 3 by 8, 2 by 8, 1 by 8, and finally it starts with 0. So these things are given to that 8 line to 3 line priority encoder. Then we can get an output as Y2, Y1 and Y0. So here the concept, it is given to an operational amplifier. Here that VA plus terminal is connected to that input signal, and the minus terminal is connected to the reference voltage. If it is the reference voltage here, this will be minus VR. If it is connected to this as the 7 by 8 VR, like that every time I am going to compare whether my analog signal is greater than this voltage. We can keep it as reference voltage. In general, I am not mentioning it as VR, 7 by 8 VR. So if I take this operational amplifier for comparator concept, I can measure VA is greater than or less than or equal to 4 by 8 VR. Like that we can compare, and we can give the outputs in terms of digital. Either if both are equal, what will be the expressions? If it is less than, it will be a 0. If it is equal to, the previous value will be maintained. So this is the concept behind this. So as I mentioned, the same flash converter to be continued here. It's the simplest A to D converter and the fastest and the more expensive one. Here the circuit consists of resistor divider network. So only I mentioned it as VR to 8 by VR, 7 by 8 VR, then 5 by 8, 6 by 8, like that 4 by 8. So then we have comparators, 8 operational comparators and the 8 to 3 line encoder. So these three are the main components to be used here, and as I mentioned, it's like a basic comparator circuit VA, and they have mentioned it as the if you are not familiar with the reference, then you can use the D terminal or VD, VD and VD. Any one terminal. For example, if VA, that is your VA value is analog signal, is greater, so I can make my logic input as 1. If my logic output is X is equal to 1. If it is less than, VA is less than VR, in that condition my X will be equal to 0. In that condition, VA is equal to VR or VD, the previous value to be mentioned. Okay, so this is the factor. Based on this, we are going to derive these factors. Okay, so in this condition, 0 to VR by 8. So in this, this is the diagram for the flash converter circuit. So here, initially it starts with 0 volt, and the voltage between is 1 by 8 VR. So in that condition, we are like mentioning it as x0, x1, x2, x3, like that. So this may be my x1. You can mark it like x0, x1, x2, x3, x4, x6 and x7. So in this condition, my 0 volt and 1 by 8 VR, and that condition I can make my output voltage as 1 the rest other voltages as zeros, because I am comparing only with the least bit of this comparator x naught. Then when it is between x 1 by 8 VR and 1 by 4 2 by 8 VR, which is nothing but is connected to x1, and it passes to the x naught and x1. So I can make this x naught and x1 to be made 1. So these are the inputs. Again it's an analog signal, assume it's a comparator signal and it's an analog signal, it is given to the encoder circuit. So it's like a discrete analog. So next it's between VR by 4 and 38 by x2 will be on. Like that I can make the expression here 1, and you can make this x2 as 1, you can put zeros here. The next 3 into VR by 8 and 4 by 8 VR or VR by 2, x3 will be on. So I can make these 4 ones, rest others are 0. Like that I can conclude So coming to this, it's like a encoder, it's like a coded bit. It starts with y0 as the least significant and y2 as the most significant. So this is the bit I have to start with 0 0 0. Next 0 0 1, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. This is like the flash converter type concept is worked. So once it gets over, it moves to that end of conversion. So next comes the successive approximation converter. So the successive approximation circuit consists of an SAR. It's a successive approximation resistor, and we have an operational amplifier, the VA. It is like a comparator, it compares the DAC value, output of this DAC is given. So you can mention it as VD, and every time it gives it expects a clock signal to be given, and it starts with the signal command, and every functions gets over, it comes to the end of conversion. So here we have a very efficient strategy to be used for the n-bit clock pulses. So in this method, an n-bit, for this is like an 8-bit register are to be used, D1 to D8. So this 8-bit register requires 8 clock pulses. So in case of n-bit requires n clock pulses. So that's the concept in this. To produce a digital output, we require whatever may be the bit, that much number of time is the clock pulses. That's the concept. Here we are going to set and correct digital representation. Then we pass this SAR registers. It may produces a digital output. That digital output is to be passed to that digital to analog converter. In that digital to analog converter, the output produced is again sent to that comparator circuit. VA is compared with VD. Then we have to give that comparator output. Okay. So initially we are going to start the conditions, and we are going to make that D1 terminal as the most significant bit. Start that condition, we are going to set D1 as the most significant bit, and they are making that other significant other bits like zeros. That means D1 is 1, the rest others will be 0. In that condition, we are going to compare your analog signal with the DAC voltages. So in this condition, if VA is greater than VD, then it makes that MSB to that 1. If it is less than, then you have to make it as the MSB to 0. That is the basic the basic comparator concept is applied here, but in case of digital and analog signals. So here a correct digital representation is 1101 0100 is given. It's like a 8-bit word is a given. Here we are going to start with my D1 terminal as the least significant bit and D8 as the most significant bit. So, making my first bit as 1 and rest other bits are 0. Now, you are comparing, this is your VD. So, consider this as your VA 1 1 0 1 0 1 0 0. So, if all the bits are 0, now these will be in equal. Here now we have only 1 1 and rest others are 0. So, by default we can say in general VA is greater than VD. So, in that condition, whenever my VA is greater than VD, I can make my MSB at left at 1, making my LSB as 1 and making the nearest LSB as 1 to make the output as 0 0 0 0. So, in this condition the output will be 1. Then next condition we will be checking 1 1 1 1. Again you can go with 0. Next concept, this is in this condition again my initial input is 1. So, now again VA is 1 1 zeros. So, again these values were greater. So, VA is greater. So, I have to make the third bit next to this, now this we call it as MSB, the next to this MSB is to be produced as 1, 4 bits, 1 1 0, 1 1 1 0, 1 more 0, right. So, now you see 1 1 0 is okay, here 1 1 0. So, 0 is smaller when compared to bit 0. So, in this condition you will be getting your output as 0. So, whenever that VA will be less than VD, you have to reset MSB to 0 and go with the next significant. So, in that condition I have to make my 1 bit as such, 1 bit as such. So, for this one and these two ones introduced, so we do not have any change in that output. Once this one and here it is 0, so 0 is less than 1, but the thing when we go for less than concept, we have to reset my MSB. I have to make this value as 0 and I have to make that LSB to that 1. Okay. So, in that condition I can write it as 0 0 0 0. So, now you compare 1 1 1 1 is greater because 0 1 0 0, here 0 0 0 0. So, now I can make my output as 1. So, now you see the next condition 1 1 0 1, the next, if it is true my VA is greater than VD, I have to make my MSB to 1. So, in that condition here the fifth bit is 0, here the fifth bit is 1. So, it is less than, now it becomes you have to make your MSB to 0. So, 1 1 0 1, you have to make this value as 0 and the next one as 1 0 0. So, now you check it is less than, you can put 0. Now, you check 4 values, 4 bits are same, now 0 1 0 0. So, in that condition what you will be getting? So, this value expression 1 1 0 1 against 0 1 0 0. So, in this it will be the same. So, now you will be getting your output as the 1. So, once it is true, you have to go with another input, this 0 1, this is maintained. So, I have to make the other MSB1 as 0. So, now it is again the output will be 0. Then again you go for this 1 0 1, this should be maintained as 0 and this should be maintained as 1. Again it will be a 0 concept. So, I have to make this 1 to be 0 0 1 0 1 0 0. So, now you will be getting a correct digital representation in this condition. So, the thing you have an SAR register, successive approximation register. So, the successive approximation register will work based on your clock pulse. How many input bits are used, that much clock pulses to be applied, and this digital signals are to be passed towards the data digital to analog converter. So, that output voltage VD is compared with that and it's given to the register comparing. So once at this end, your end of conversion comes. So you initially are starting, next you are applying your DN as the MSB bit, it's a 1 initially, then you are going to process your voltage. VA is compared with VD. If VA is greater than VD, you have to set your MSB value as 1 and rest others, and make the next LSB to 1. So far we have discussed ADC and the DAC. In the DAC we have seen two types. One is direct type DAC and the integrating type DAC. So far we have seen a flash type, and the successive approximation resistor type comes under the category of digital type, it's direct type DAC. So it's not a DAC, it's ADC. Integrating type ADC. So in this integrating type, as I mentioned, the direct type, when an input signal is applied and we have an inbuilt reference signals. So in this inverting type, the conversion will be in an indirect manner. An analog input signal is converted to a linear function that may be of time or frequency, and then it is converted to a digital code. So analog to digital conversion takes place. So here a dual slope ADC. So the dual slope ADC has two operational, it's like a operational amplifier, and this A2 operational amplifier is applied for that integrator concept. That means your feedback resistor is connected with the capacitor, and the input resistance is connected to that inverting terminal. Here we have a control logic, and we have n stage counters. So that inputs like digital inputs like D1 to Dn are to be connected to that n stage counter. It depends on that control logic. This uses the start and the end of conversion concept, and it is applied to that voltage comparator. Here the non-inverting terminal is to be grounded. So here the integration. So here the inverting terminal input signal, the analog signal VA is applied, and the reference signal which is of opposite polarity. So the concept behind this A1, here we are going to integrate the VA for fixed duration of 2 power n clock signals. So the main thing we are going to discuss with the clock periods, that VA to be integrated for 2 power n clock periods, and the VR to be used for the n clock signals, that is n clock signals. So in this, first every time we have to trigger that circuit, so we use a start command. So once you use a start command, this switch SW1 is to be grounded. So in that condition, your switch is grounded, then SW2 is to be closed. So when it gets closed, that A1 and A2 has an offset voltage after integration, that CAG, that is nothing but the capacitor with auto zero correction. It produces the input offset voltage of all the 3 amplifiers. So the offset voltage, as we know that when we apply an input voltage as 0, we expect that output voltage to 0, but in this condition we can't say that V0 will be a 0 volt. So that we are making adjustments as auto zero corrections. So that is the condition. In the second condition, now my switch, earlier condition, my switch 2 is closed. That's other condition, my switch gets opened, then CAG acts as the memory to hold the voltage. It's like it holds the value of that, and it stores in the memory to keep that offset null. Null means it's like a 0 voltage. That is the condition. So now I explain this with the diagram concept. So here it draws with the characteristic curve with the time versus the output voltage V0. So in this, from 0 to T1, we will be doing that auto zero correction. At T1, the switch SW2 opens, and the SW2 gets opens, in that condition my SW1 gets closed and it is connected to the analog signal. So, here that analog signal is already I have mentioned, it integrates for the clock period T1 and the integration takes place for the analog signal. So, in that condition the integration of VA, the output produces a ramp signal, that too with a downward direction. Okay. So, it is like a linear curve with a negative direction. So, the second condition, now it reaches some particular time period at time t. At time t is equal to T2, in that condition again my SW2 opens. Here that SW2 opens and it is connected to the reference voltage. So, here the reference voltage is like already I have mentioned, VA with the polarity of plus minus, VR with the opposite polarity. So, again it starts increasing the operation, again the integration of that reference voltage takes place. It is in the opposite direction, the ramp signal, it reaches T3. So, in this condition at time T3 it ends the conversion. So, now at T2 to T3 we have only the n cycles for the integration of this reference voltage. At the integration of the analog signal we have 2 power n into t signals. So, coming to the derivation part, we can mention that T1, capital T1 is the difference between T2 minus T1. We can mention 2 power n count by clock rate t. Similarly, T3 minus T2 is like digital count by clock rate. So, I can mention this is the voltage for the V1. So, V1 is equal to the integration of your analog signal can be written as minus 1 by RC into VA of this time period T2 minus T1. This is the general expression for this integration circuit. So, now for this part alone between your time T1 and T2, I can write VA of T2 minus T1. So, in this T2 minus T3 minus T2, V1 is equal to, this is for the reference voltage, this part is the integration of the reference voltage part. So, minus 1 by RC of minus VR of T2 minus T3. Again I can write T3 minus T2 based on this negative signal is taken. So, now I am going to equate these V1 and V1 signal. So, minus 1 by RC and 1 by RC gets cancelled. VA of T2 minus T1 is equal to VR of T3 minus T2. Then T2 minus T1 is equal to 2 power n by t or else n by t. Based on this TT gets cancelled. So, 2 power n equal to VR by n. VA is equal to VR by n by 2 power n. That is the final expression for the analog signal in case of that integrating type ADC. VA is equal to the reference voltage into the clock digital count by 2 power n counts. VA is equal to VR of n by 2 power n.